If you step barefoot onto a freshly paved parking lot in mid-July, you feel the heat instantly radiating up into your feet. That burning sensation happens because dark materials actively absorb solar radiation, trapping the sun's energy instead of bouncing it away. Now, picture millions of microscopic fragments of that exact same dark, heat-absorbing material, completely invisible to the naked eye, drifting freely through the air we breathe. The physical process you feel on the pavement provides a window into a similar phenomenon occurring in the sky, where researchers have identified a layer of microscopic particles that act as a heating agent for the planet. For decades, scientists have meticulously measured standard atmospheric pollutants. We have precise tracking mechanisms for carbon dioxide, methane, and the soot produced by burning fossil fuels. Those measurements feed into massive global climate assessments, like those published by the Intergovernmental Panel on Climate Change, which establish our baseline understanding of global warming. In parallel, ecologists have spent years mapping physical plastic pollution as it accumulates in our rivers, soils, and ocean currents. But a study published in Nature Climate Change by researchers at Fudan University identifies a point where these two previously separate issues overlap. Instead of remaining trapped on the ground or in the water, synthetic fragments are flowing into the atmosphere, where they function as an active, unaccounted-for heating agent. High above the surface, microplastics and nanoplastics, broken-down bits of synthetic waste, have infiltrated global air currents. In the atmosphere, microscopic fragments handle sunlight based on color. Lighter particles act like mirrors, reflecting solar energy into space. Darker particles behave like asphalt, absorbing and radiating heat. Simulating this globally, the Fudan study estimated microplastics' warming abilities outweigh their cooling effects. Through decades of synthetic waste breakdown, humanity inadvertently filled the sky with a microscopic heat-trapping prism. To understand the implications for the climate, we have to quantify how much extra energy this layer is generating. Climatologists typically measure severe atmospheric warming against a baseline known as black carbon or soot. The research provides a striking comparison. Airborne microplastics currently exert a warming effect equal to approximately 16% of that caused by black carbon. This 16% is an unaccounted-for addition to the global temperature rise we are already experiencing, a source of heat that isn't yet factored into international climate assessments. The result is a planet being insulated by an invisible layer of microscopic trash. This finding has immediate consequences for the Intergovernmental Panel on Climate Change and the frameworks they use to predict our future. Currently, 0 of the major climate models factor in the 16% extra heat generated by these plastic particles. The researchers argue that these models must be updated. Predicting global temperatures is impossible if scientists ignore a heat-radiating variable drifting through the atmosphere. However, mapping this impact is a significant challenge. As researchers at Duke University point out, we still lack data on the exact horizontal and vertical distribution of these particles worldwide. Until we can accurately map the plastic in the sky, our climate predictions will remain incomplete. While the warming happens in the sky, the problem begins where these materials are first synthesized. Plastics are manufactured from the byproducts of fossil fuel production. Every synthetic fragment in the atmosphere is a derivative of petroleum. The carbon footprints of these materials starts at the refinery, continues through their use, and ends with their newly discovered afterlife as a sky heater. As microplastics researcher Steve Allen notes, the goal is to evaluate the total carbon emissions throughout the entire life cycle of plastic production. Plastic functions as a global, end-to-end climate driver. Because the warming begins at the factory and continues as the material breaks down in the sky, the most effective way to remove this heat is to reduce reliance on the material entirely.